Hello, in this video we will do a short review on vector and inner product spaces. I will not do theoretical and practical separately. I try to remind you theoretical based on examples. Okay, we have matrix A as you see in your screen 3, 4, 10, 1, 5, 6, 1, 16, 14. We have to find a basics for the row space, for column space, and for the null space. Those are three main spaces associated to a matrix. Okay, so what are they? If you have matrix A with m rows and n columns, so you can consider A as a map from Rn to Rm. Why? Look at this. So you have row 1 in here, row 2, R1, R2, and so Rm. And then you have the first column in here called C1, C2, and Cn. If you apply this matrix to some vectors, right? To some vectors in here. So you suppose you have x1, x2. So this vector should have n coordinates. I mean, you stop at xn. Otherwise, you just cannot multiply the rows, right, with this vector. Make sense? So at the end, you get some vector with y1, y2, and then ym. So I hope you still remember the situation when we study system of linear equations, right? We have m rows means we have m equations. We have n columns means we have n variables. So basically, a matrix M by N can be considered as a map from Rn to Rm. Okay? And then rows, you can see from here, rows are vectors in Rn. Is it correct? I can write here rows. They are vectors in Rn, and columns, they are vectors in Rm. And then once you have vectors, a set of vectors, you can consider subspaces generated by those vectors. So you have a linear spans of all rows and linear spans of, or I can write, let's use this, span and span of columns. Make sense? And all possible linear combinations of rows and columns will form subspaces in their spaces. So we have one subspace in here, we have another subspace in here. Once you have subspace, of course, you have right to consider a basics for that space. Make sense? So you need to learn basics. You need to learn dimensions, right? With the basics, you can do coordinate. You can express any vector as a linear combination of basics, and you get coordinates of that vector with respect to that basics. Make sense? Okay, that is the one thing. So we have row space and column space. How about the null space? Here we have Rn, and here we have Rm, two spaces, and here's the map A. Here you have vector 0. The null space of A is nothing but the set of all vectors in Rm such that Ax equal to 0. So that means, the matrix A sends all vectors right here to 0, vectors in Rm. That's it. That is the null space of A. Okay, and again, the null space of A is a subspace in Rn, not in Rm. Don't forget that. And based on this theoretical review, in order to solve these questions, we need to get a reduced row echelon form of A. Okay, so that is the case. You need to get the reduced row echelon form of A. Let's do that together. So we just need to use row elementary operations. So I have 3 in here, 4 in here, 10 in here. I have 1, 5, 6 in here, and 1, 16, 14 in here. I will do the following way. You know, for the purpose of this problem, we might interchange rows because you want to have leading element equal to 1, right? Here you have 3. It's not very good for computation. So basically, I just interchange the first row and the second row, okay? Or, you know, in general, you don't have to do that. Let me show that to you. So I will keep the second row, or maybe I keep the third row. Let's do that. Let's keep the third row. And I multiply the third row by -1 and add to the second. I get 0 in here. I get -11 in here. And I get -8. I multiply the third row by -3 and add to the first. I get 0 in here. -3, I get -48. Plus 4 is -44. And then -3 with 14, I get 42. 42 minus 42 plus 10 is -32. And you can see that, you know, the second row and the first row are just scalar multiple, right? You multiply the second row by -4, add to the first, you get the following one: 0, -11, -8, 0, 0, 0. So you can see some row echelon form, right? Some row echelon form, not in a standard way, but anyway, you have that. You have like this. You see this? From this form, I can make my decision. Okay, the row space. I can pick 2 non-zero rows in here, and they form a basics for the row space. All right. For the column space, I repeat again, but I cannot pick this vector and this vector. I have to pick the original columns corresponding to these 2 columns. Because we do row elementary operations, we already change columns. Make sense? So if you pick these 2 vectors, you will not keep the same column space. So I have to pick the original vectors. That means I have to pick this guy, okay, and this guy. So I can write in here. That is 3, 1, 1, and 4, 5, 16. Make sense? So these 2 vectors will form a basics for the column space. I repeat again, for rows, you can pick vectors at the end, right? Because you do row elementary operations. You don't change the row space. But for columns, you need to choose the original vectors. All right, so now let's work for the null space. For the null space, you have to solve the homogeneous system. From the very last form in here, you have to solve the following homogeneous system. I write here with the null space. You set x1 plus 16, x2 plus 14, x3 equal to 0, and negative 11x2 minus 8x3 equal to 0. Okay, so from the second equation you solve for x2, you get negative 8 over 11x3, and then you plug this into the first equation, you get x1 is equal to negative 16 x2 minus 14 x3, which is equal to negative 16 times negative 8 over 11 x3 minus 14 x3. You get plus plus, so you have 8, and then 128 over 11 minus 14 multiply with x3. So you just simplify this. Okay, let me do this in here. 11, 14, so I have 14 and 10, 11, I have 155. So basically that is minus 155, 128. Okay, so you get 23 negative. Okay, so you get negative 23 over 11 x3. All right, so you already solved the homogeneous system. You can write the general solution in the following form. The solution, that should be negative 23 over 11 x3, negative 8 over 11 x3, and x3. Or you can write x3 over 11, negative 23, negative 8, and 11. So what does it mean? That means the null space contains all vectors of this form. That means this vector is a basis of the null space. Okay, and this is the basis of the null space. So we are done. Let's consider the second example. Transition matrix. You have one basis of R2, let's say in R2. You have B1, negative 2 and 1, 1, negative 1, and B2 is 0, 2, 1, and 1. It's easy to verify that B1 and B2 are bases for R2. And now we need to find coordinate of vector x with respect to B2. If we know the coordinate of x with respect to B1 is 4, negative 5. You can write transpose in here. When you move from one to another basis, the coordinates will change accordingly. You have to find coordinates in the new basis. You just need to find the transition matrix from one basis to another. Once you have that transition matrix, each time when you want to find coordinate of a vector with respect to a new basis, you just apply the transition matrix to the coordinate in the old basis. All right? So in order to find transition matrix from B1 to B2, I do the following way. I write B2 in here and then B1 in here. I will use row elementary operations to get the form identity. I write in general IN, and here is my transition matrix. Make sense? You know, basically doing this, we are solving two or n systems of linear equations at the same time. Okay? So basically we express vector in B1 as a linear combinations of vectors in B2. That is the meaning of this. And that is the meaning of the transition matrix. Okay? So let's solve this problem. I write in the column form. Don't forget that. In the column form. So I write B2 in here is 0, 2. In here I have 1, 1. In here I have -2, 1. And 1, -1. Okay. So I need to make, I need to get an identity matrix in here, I2. So since we have 0 in here, we just add the second to the first. Okay, so I get 2, 2, -1, 0. And here you get 2, 1, 1, -1. And then I multiply the first with -1 and add to the second. I get 2, 2 in here. -1, 0. I get 0. I get -1. I get 2. I get -1 in here. Okay, that is -1 multiplied with -1. Add to the second row. So after that, I have -1 in here. I just multiply the second row by -1. I get plus, negative, and then plus in here. Okay, and multiply the second row by -2. Add to the first. I get 2 in here, 0. -2 add to the first, I get 3. -2 add to the first, I get -2. In here I have 0, 1, -2, and 1. And now I divide the first row by 2. I divide by 2, I divide by 2, I divide by 2. This is my transition matrix from B1 to B2. Okay, once you have the transition matrix, you can find the coordinate of x with respect to B2 equal to this matrix, 3, 2, -1, and here -2 and 1 applied to the coordinate is 4, -5, and you get what you need. For the first one, I get 5 plus 12 over 2. That means I have 22 over, I get 12 over 2 is 6. Yes, 6 plus 5 is 11. I get 11 in here. And in here I get -8 with -5 is -13. So we are done with this problem. Of course, if you have the transition matrix from B1 to B2, you can find the transition matrix from B2 to B1, right? Let me remind you about that. So the transition matrix from B2 to P1, that is just the inverse of the transition matrix from B1 to B2. Okay, that is very simple. And for 2 by 2 matrices, you have the formula of the inverse. If you have matrix A equal to A, B, C, D, and A is invertible, you can find the inverse matrix as 1 over AD minus BC times D, A, -B, and -C in here. All right? I just remind you the formula in case we need in the future. Example 3, with subspaces. Suppose you have a subset, and then you want to consider if this subset satisfies 10 properties of a vector space or not. You don't want to check all of them. You just need to check 2 properties. The first one, this set should be closed under addition. Right? What does it mean? That means you pick 2 vectors U and V, you add them, so you have a set in that. That means you pick 2 arbitrary vectors in S. The sum is also in S. And this should be closed under the scalar multiplication. So what does it mean? That means you pick some vector, you multiply with some scalar, you still have a vector in that set. So once the set satisfies two properties, that will be a subspace. So we consider the set of, or the vector space of n by n matrices and some set V in this, such that V is all matrix A and A is commuting with a given matrix B. So I will write, yeah, A B0 equal to B0A. Or I can write here V B0. Means they give you a matrix B0 and they consider the set V B0 which contains all matrix A that commuting with B0. And you need to check that if this is a subspace or not. Okay? So let's check if VB0 is a subspace or not. We need to check two properties. The first one, you pick some vector matrix A, 1 and A2 in V. Okay, so you have A1 B0 plus equal to B0 A1 and A2 B0 equal to B0 A2, because they are vectors in V B0, sorry. And then you sum them up, right? You sum them up, you need to check A1 plus A2 B0, and this is equal to B0 A1 plus A2. And you know, this is a consequence of these two identities. So what does it mean? That means A1 plus A2 is commuting with B0. From here I get A1 plus A2 is also a vector in, is also an element in VB0. So the first property is good. The second property, you pick some matrix A, some lambda, and then you consider A lambda. And you need to check if A lambda belongs to VB0 or not. So that means we need to check the following identity. B0 lambda A. Right? But this is also obvious. Why? Because lambda is just scalar. Lambda is just scalar in here. So you can take this out, right? And you get just lambda A B0 from the left-hand side. Since A B0 equal to B0A, you get lambda B0A. And since lambda is the number, you can take that in, you get B0 lambda A, which equal to the right-hand side part. So basically, yes, the set VB0 is a subspace for each B0. Example 4, spanning set. They give you S, which contains two vectors, 1 and -2, -2 and 2. Okay, they ask you if this set span the whole R2 or not. It's pretty easy. You know, R2 has dimension 2. This set has two vectors. So S spans R2 if and only if vectors in S form a basis for R2. So basically you need to do very simple thing. You said you consider the matrix 1, -2 and -2, 2 in here. You write vectors in the column form and you check the determinant. Make sense? If the determinant is 0, that means these vectors are not linearly dependent, are not linearly independent. They cannot form basics because they have only two vectors. So you say no. If the determinant is 0, that means not 0, sorry, these vectors are linearly independent. Two linearly independents will form basics for R2. So say yes. So what is the determinant of this guy? That is just 2 minus 4 equal to -2, which is not 0. So you can see your answer right away. All right? Spanning set in R3. Okay, so you have set S is 1, -4, 0. Another one is 0, 0, 1, and -1, 4, 0. You do similar steps like previous example. You write these vectors in the column form or in row form. Yes, in this situation, row form also work. -1, 4, and 0. And you check the determinant, right? Because you have matrix 3 by 3. You know, each time when you have 3, when you have a square matrix, that situation is not difficult because most of the times you can check using determinant. Okay, so you find determinant of this matrix. If the determinant is 0, no. If that is not 0, yes. Okay, so what is the determinant of this matrix? I will span the determinant along the second column because I have 2 zeros out there. So the determinant of this matrix A is just equal to, this position is 3 by 2, so I have -1, and here 1, -1, -4, and 4. The determinant is 0. So that is no. S does not span R3. You have a set S, -3, 1, 3, and then 1, 9, -3, and then 2, 4, -3. They ask you to check, to determine if S is linearly independent or not. Okay. Again, you write them in a row or column form. It's okay. You have matrix 3 by 3. This is 3 by 3. For square matrices, you can check determinant. If the determinant is 0, rows of this matrix are not linearly independent. If the determinant is not 0, they are linearly independent. Is it? So your job is just to find the determinant. Okay, so let's find determinant of this matrix A. We have different methods to find determinant. Okay, I will do the following way. I will use diagonal form. So I have -3 times 9 times -3 minus 1 times 2 times 3 plus 1 times 3 times 4. And then with the other diagonal, I have -2 times 3 times 9. And then minus -3 times -3 times 4. And then minus 1 times 1 times -3. Let's simplify this and see if this guy is 0 or not 0. So I have 6 in here, -6. This guy, with this guy, I will get -3 times 9, which is 27. If I compile these two terms together, 6, and here I have 12. -20, 27, -6 and 12. So I have 6 in here. Basically, on the top, you have -21, okay? And here you have my 9 with is 36 with the negative. In here you have plus 3 minus 21. So basically the determinant is not 0. You can use calculator to find that easily. So since the determinant is not 0, that means the matrix is invertible, right? All rows are linearly independent. So that is the final answer, linearly independent. Now we deal with the space of polynomials, P2. That is the vector space of polynomial with degree less than or equal to 2. So basically, you have all form A, B, C, or ax squared plus bx plus c. Don't forget that, this vector space is the same with R3 because you need 3 numbers, right, to determine a such polynomial. All right, so they give you S, which is 1 minus x, and then 1 minus x squared, and then negative 1 minus 6x plus 7x squared. They ask you to determine if S is linearly independent or not. If S is linearly independent, S will span the whole P2. Is that correct? Because we have 3 vectors and they are linearly independent. P2 has dimension equal to 3. Okay? So in order to solve this problem, I really recommend you to use this relation. So you convert your vectors, your polynomials into vector form. Okay, so you may pick like ax squared plus bx plus c, or you may choose like a plus bx plus c x squared. That is your choice, but you have to do the same thing for all polynomials in here. So let me pick a x squared plus bx plus c. For the first polynomial, I get 0 because I don't have x squared there, negative 1 and 1, right? For the second one, I get negative 1, 0, and 1. For the last one, I get 7, negative 6, and negative 1. So if these 3 vectors are linearly independent, 3 polynomials in S are also linearly independent. If not, they will be linearly dependent. Okay, so basically you need to check the matrix, the determinant of the following matrix: 0, negative 1, and 1, negative 1, 0, and 1, 7, negative 6, and negative 1. You check the determinant of this matrix because you have square, which is good. So if the determinant is 0, linearly dependent. If the determinant is not 0, linearly independent. Make sense? Okay, so let's find this. I have 0, 0, negative 1, which is 0. Negative 1 with 1, 7. I get negative 7. Negative 1, negative 6 with 6. With 1 is just 6. And then another one is 0 with the other diagonal right here. So I have 0 and minus negative 1. So basically I get 0. So from here, these vectors are not linearly dependent, right? Linearly dependent. And so these polynomials are also linearly dependent. They will not span the whole space P2. Now let's talk about inner product spaces. When we study vector spaces, we don't have any geometry of the space because we didn't have any measurement. Make sense? But for inner product spaces, yes, we have measurement because we have inner product out there. So what are inner products? If you have some vector space V and you consider some map from the Cartesian product VV to R. I consider just R. Sometimes, you can consider C, but, if you consider C, some properties will be changed. And this this map should satisfy three properties. If you have UV, that is also VU. Okay. When you multiply with some scalar, that is CUV, and at the same time that is UCV, and the last property is U and U is always greater than or equal to 0. Equality happens if and only if when U is equal to 0. So these are three properties for a map to be an inner product in V. Okay, once you have inner product, you can use this inner product to generate a distance norm. So you have a norm that is U equal to UU square root. You have distance between two vectors U and V, that is the norm of U minus V. You can determine the angle between them using the following formula: cosine theta equal to inner product divided by the norm of U divided by the norm of V. And then you can determine orthogonality. You say two vectors are orthogonal if their inner product is 0. Once you have orthogonality, you can use Gram-Schmidt process. Gram-Schmidt process to find an orthonormal basis. Normal basics from any basics. Makes sense? So that is the whole geometry of an inner product space. Okay, let's consider the following example. It's just very basic. You need you have two vectors -1, 8, and V is 8, 9. They ask you to find the norm of U. Pretty simple. That is -1 square plus a square, and then apply square root, which is square root of 65. Now in this case, the inner product space is dot product. If we don't say anything about spatial inner product space in Rn, right? That is just dot product. You can find the norm of V, square root of a square plus 9 square, which is 64 plus 81 square root, and then you get 145. Okay, you can find the distance between U and V, which is the norm of U minus V. So you can write the norm of what? Of 9 and here 1, and that is square root of 9 square plus 1 square, which is square root of 82. You can find the angle between them. Cosine of theta equal to U in the product with the V divided by norm of U and norm of V. That is what? That is -a plus 72 over the norm of U. What is the norm of U? We have this right here. That is square root of 65 times square root of 149. So you get 64 over square root of 65 times square root of 145. And once you have that, you use calculator to find angle theta, which is a cosine of 64 over square root of 65 times 145 here. That's it. Okay, and of course in this case these two vectors are not orthogonal because the dot product is not 0. Done. All right. Before we move to Gram-Schmidt process, we need to remind you about orthogonality, how to find orthogonal projection of one vector onto another one. Okay, using these two vectors, we can do that. Let's find orthogonal projection of U onto V and orthogonal projection of V onto U. So according to the formula, we have UV in here and then divide by the norm of V squared times V. And here is UV, the norm of U squared times U. Okay, so we already have that product, which is 64, right? And the norm of V is 154, I guess, 145. 145. You know, we apply squaring here, so you don't have square root anymore, right? Times V, which is 8, 9. And another one, I have 64 over 65 and negative 1, 8. So you see, it's pretty easy, okay? All right. Another important property of inner product space is orthogonal subspace. So what does it mean? I mean, you have the whole space right here, okay? You have some vector in here and you have some subspace in here. You need to find orthogonal projection of this onto that subspace. Or sometimes you have to determine the subspace which is orthogonal to some vector or to some other subspace. Make sense? You know, that is very important problem. Actually, that is some kind of optimization problem. Let's consider the following example. You have vector U in R3. They ask you to find the subspace in R3, which is orthogonal to U. So you can imagine, right? You have R3 in here, you have some point right here, or you have some vector, right? And you need to find all vectors in R3 such that you need to find the subspace in R3 which is orthogonal to V. So you can imagine that should be planes, right? There should be planes. But be careful with this. You know, we cannot just say, yeah, all vectors, you know, are orthogonal to this guy. They will not form a subspace of R3. Don't forget that. Because our subspaces should have 0. Makes sense? So basically they should pass through the origin. All right, so we can solve that easily. So I can pick x1, x2, x3 as an arbitrary point in R3. And I will take dot product of x and u, and I set it equal to 0. Doing so, I can find all x1, x2, x3 such that x is orthogonal to u. So I have x1 minus 3x2 plus x3 equal to 0. So that is the whole plan. You know, if you want to write in an explicit form, I need to solve this system, right? Actually, the system has only one equation, but it's fine. You already know how to solve homogeneous system. You write x1 equal to 3x2 minus x3. And the general solution, that is just 3x2 minus x3, x2 and x3. Or this is a linear combination of 3x, okay. Or this is just linear, All this is just a linear combination of 3, 1, 0, and -1, 0, and 1. You see? And these two vectors form basics of this subspace. If you want, you can check that. Actually, these two vectors are orthogonal to vector u. Just check the dot product. Agree? All right, so let's move to the last problem. Gram-Schmidt process. Now we already know orthogonality. We already know how to find orthogonal projection. Let's talk about Gram-Schmidt process. The main idea of the Gram-Schmidt process is the following. You have vector u1, u2, and un. And this n vector form a basics for your vector space. They are not orthogonal. They are not normal. Not orthogonal. Not normal. That means the norm is not 1. Okay? You want to get an orthonormal basics. We already discussed about that because those basics are really good and really easy to hang out with them. So, how do that? I fix one vector v1 equal to u1. And then I move to the second one. I denote by v2 as v2 minus orthogonal projection of u2 on v1. I keep v1 in here, okay? And then I move to the next vector. I pick u3 minus orthogonal projection of u3 on v1 and minus orthogonal projection of u3 on v2. I keep v1, v2 in here. So basically, I continue this process until I get vn equal to un minus orthogonal projection of un onto v1, orthogonal projection of un onto v2, minus and so on, orthogonal projection of un onto vn. Make sense? So basically, how to say, the whole process, how to describe the whole process in one sentence. The first step is fixing one element. The next step, subtract from the second vector x orthogonal projection on the previous vector. You move to the next step, you do almost the same thing, subtract the next vector. Subtract from the next vector x orthogonal projections onto previous vectors. But previous vectors means, v1, v2, v3, and so on, not the original vectors. Make sense? By doing so, you get an orthogonal basics. Because at the end, you get an orthogonal basics. And from an orthogonal basics, you can normalize them. Means you divide each vector by their norms to get orthonormal basics. Make sense? All right, let's consider the following example, which is 0, 0, 8, 0, 1, 1, and 1, 1, 1. It's easy to verify that B is a basics for R3. And they are not orthogonal. They are not orthonormal. All vectors are not perpendicular with each other. Okay, so let's denote by u1, u2, and u3 in here. I will fix V1 equal to U1. And then V2 equal to U2 minus orthogonal projection of U2 on V1. That is 0, 0, 8. I have U2 is 0, 1, 1 minus orthogonal projection. That is just 0, 0, 1. Dot product with 0, 0, 8. Oh no, here I should have 1 right here, okay? And then divide by the norm of U1, the norm square, which is 8, times 0, 0, 8. So I get 0, 1, 1 minus 8 over 8, 0, 0, 8, which is 0, 1, and negative 7. Okay, and then I move to V3. I have V3 is 1, 1, 1 minus orthogonal projection of this vector onto V1 and V2. So I have this is 0, 0, 8. The norm is 8. We already see that. Times 0, 0, 8 minus another orthogonal projection 1, 1, 1 times 0, 1, negative 7. So I have to pick this vector. You see, I have to pick this vector, right? And divide by the norm of this guy square. So I have 1 square plus 7 square times 0, 1, negative 7. At the end, I have 1, 1, 1 in here minus. This gives me again 1. So I have 0, 0, 8 minus. I have 1, negative 7 minus. So I have negative 6 in here. And here 40. I have 50. And here 0, 1, negative 7. Let's simplify them. For these two vectors, I get 1, 1, negative 7. And for this guy, I plus 0, 3 over 25. And then negative 21 over 25. So I get 1, 28 over 25. And then negative 7 with 25. I get 7 in here, negative 7, 1 plus 3 over 25, which is 28 over 25 times 7, which is not good. Not a good number. So I have 7 times 28 over 25. That's fine. You know, the most important is the idea, right? So once you have all computations, you have this, the last vector. You divide V1 over the norm of V1. You get V2 over the norm of V2. And you get V3 over the norm of V3. And then you get orthonormal basics. That is how the Gram-Schmidt process works. Okay? I think I finished my review. So I recommend you to solve all this problem again. I may do some mistakes in computation. Just let me know if you see any. Okay? And if you have any questions, feel free to let me know. All right? Thank you.